Morning, guys.
Morning.
Morning. Now, before we start, does anybody have any questions? Any questions, concerns, things you want to clarify before we continue? No. Okay. So we're going to start with chapter number 12, which algorithm is okay, just says okay, two-dimensional imaging. Later on, we will be talking about yes, okay, what is going to be 3D imaging as well. But anyways, good. Okay. Now, guys, what we mainly see on a scan is mainly going to be as okay, regular 2D imaging. Okay, mainly because okay, we have one dimension and we have another dimension. Okay. Now, these images need to yes, okay, for an image like this, or even yes, okay, for instance, okay, for an image like this, or for an image like this, or for an image like this. To be formed, there's mainly going to be two things that need to be overcome. One issue is that, okay, as we know, that sound waves travel straight. Okay. Now, first thing is that, okay, as if sound waves travel straight, how would they be able to, yes, okay, get to a narrowest point, which we'll call the focus? Okay. Likewise, if for instance, okay, this was your transducer. How is it that we get, for instance, okay, this part of the image or this part of the image as with the sound beam only traveled straight? Okay, so these are some of the points that okay, as we will be talking about in this chapter. Okay, now if we for instance okay take any image shape, let's see that we have for instance okay this one. Now what do we have? We can say okay, this is the transducer. Now what this transducer here mainly is okay will have is going to be multiple PCTs. So each of these here is okay is going to be, yes, okay, individual PCT. Okay. Now, guys, we can mean it's okay, just label them and say 1 followed by 2 followed by 3 4 5 6 and 7, just for an instance. Okay, guys. Now, how is that is going to mainly as okay produce an image is, now since we just labeled this one has 1, that is going to fire first. Okay, all the way to okay to the depth and okay has received the reflections, followed by then this one here is okay, maybe firing next, followed by this one here is okay next, and so on. Okay, so that's going to be as okay one of the things that we will be talking about, but it's going to be as okay in cases that each the transducer has more than 1 crystal or 1 PCT. Okay, so okay, so in the case that we had is okay, let's say it's okay. In this case, we just have 7. And it's going to be more than 7. It's going to be several hundreds, but okay, yes, okay. But there's going to be as okay a certain sequence in which the PCTs or crystals are going to be firing. Clear? Okay, and that sequence is mainly as okay going to determine the direction in which the beam is going to be steered. That sequence determines the direction in which the beam will be steered. Okay, and mainly as okay causes, because that's okay the image to form or go as okay, that's okay, be made the way that it is. Clear? Okay. Likewise, yes, okay, in most of our transducers, yes, okay, where we had multiple focal points. Okay. And what we said was, okay, that autoimmune is okay called array focusing. Okay. In most of the instances, in most, there's one exception, is that okay, yes, that this focal point, these focal points here are going to be as okay controlled electronically. Okay, whereas okay, we only had one fixed focal point. Because mainly says okay, 2 things either is going to be okay, the size of the PCT that will determine the focal depth or focal point. Right, okay. Did that make sense? Or, yes, okay, and or, yes, okay, because that's okay, the curvature of the PCT, if we said that we had internal focusing, or the curvature of the lens, if we said that we had external focusing. Okay, but for most of our array focusing transducers. That's going to, yes, okay. That focus is going to be controlled electronically. Okay. Whereas if we had fixed, it could be as okay the size of the PCT. It could be as okay depending upon as okay the curvature of the PCT, which we had okay as an internal focusing, or as okay the curvature of the lens, which was okay as an example of external focusing. Okay. One thing, and especially as okay when we talk about as okay the electronically. Okay. Now there's going to be as okay mainly two things that will be as okay controlled electronically. Is going to be the focusing of the beam and the next is going to be as okay what we'll call the steering of the beam. Yeah, okay. That will be controlled electronically, especially as okay in transducers where we have multiple PCTs or crystals. Okay. So although this was all transducer, but it can produce an image which is going to get or be wider than the actual footprint of the transducer. Because some transducers have a small footprint, but then actually it's okay be able to scan greater and greater and greater areas than the footprint. And that mainly is okay requires that the beam get steered. Right. So both of these processes is going to happen electronically. So steering of the beam and it's okay the focusing. Here we have multiple PCTs lined along the footprint from yes, okay, left to right. Okay, guys. Now, as far as transducers are concerned, we can see that we have two major types. We got two major types of transducers. Pulse wave transducers and continuous wave transducers. Now, what is the main difference between these two here? Is there anybody? would like to tell me what is the main difference between these two here?
Continuous wave are therapeutic. Pulse waves produce an image.
Okay, good. So we could say that, okay, this one here was also called therapeutic transducers, where these were imaging transducers, right? Okay. Okay. Based on this, we could also say that, okay, yes, this one here was a non-imaging transducer. Okay. But mainly it's okay. Structurally, it's okay. What we could say about is that's okay. That pulse wave transducer had backing material. Where no continuous wave transducers have no backing material. Okay. Now, if you look at this chapter here, it's okay. What is it that it talks about? It says, okay, as it said, 2D imaging, right? Okay. So that mainly means, okay, more and all of the translucent that we're going to be talking about in this chapter here are generally, it's okay, going to be pulsed wave transducers. Okay. And one thing that you should remember is, okay, whenever you see the word pulsed or pulsed wave, next thing that should come to your mind is, along with pulse, is going to be, it's okay, PRP and PRF. Okay. But generally, guys, it's okay, the kind of transducers that we will be talking about in this chapter here all are going to be pulsed wave transducers. Okay. Now, guys, what we mainly can do is that we can say that, okay, yes, how will we classify them? Oops. So we could say it's okay, pulsed wave transducers. Now, the way that we may classify them here is going to be, because it's okay, based on number of focal points. So the first transducer that we will have is going to be, it's okay, what we'll call a mechanical transducer. And this mechanical transducer here is what we briefly, as okay, I talked about in the previous chapter where we say, okay, one fixed focal point. Where we, as okay, back then said, okay, as that focusing for this one was going to be mechanical. Not just that, but that we just had one fixed focal point. Okay. The other kind of transducers that we will be talking about is going to be, as okay, what we call array transducers. And what did we mean by array transducers? These were going to be, as okay, transducers with multiple focal points, where we were not stuck to one fixed focal point, which was determined by the transducer, but where we actually, it's okay, were able to focus at multiple focal points. Now, guys, I know that, okay, yes, in your book, the sequence of, yes, okay, your array transducers is a little bit different from the way that I would go. But I would mean, yes, okay, go on and start first off with what we call the annular array transducer. Followed by a linear phased array transducer. Followed by a linear sequential array transducer. Followed by, now this one here has a bunch of names. It can be called curved. It can be called a convex. Or it can even also, yes, okay, be called a curvilinear. And of course, yes, okay, each of these can be followed by the word array transducer. So it can be called a curve array transducer. It can be called a convex curve array transducer or the curvilinear array transducer. And last but not the least is going to be, yes, okay, what we call the vector array transducer. Okay, guys. So this is pretty much okay as just a list of your transducers. Okay. In the way that we will be talking about. Okay. And for each or most, okay, there's an exception here, but anyways, for each of these transducers, okay, that means it's okay going to be, that's okay, 5 similar points that we will be talking about. Yep. Any questions so far? Okay. So one thing too is okay, just take away for now is that the word array mainly is okay, just meant multiple focal points and or yes, okay, adjustable. And I hope that you guys, okay, the other day saw as okay how we could adjust the number of focal points from 1 to 2, 2 to 3, 3 to 4, and so on. But also as okay, we're able to as okay move those focal points to shallower depths or to deeper depths. Yeah, okay. Mainly as okay by that far right knob. And okay, it's in your B mode. In B mode, that's okay. It had 2 functions. It had, it's okay, focus num or focus pause. And what I said was that whichever was locked in the bracket was inactive as far as the law was concerned, whereas the one that was outside the bracket was going to be the active function. The way to switch this into the bracket and this one out of the bracket was mainly it's okay, just going to be done by slightly pushing on the button. Yep. Now, guys, the 5 points that we'll be talking about for our transducers are going to respectively be as okay the number of PCTs. Now, please keep in mind, as okay, this is the chapter where they actually, as okay, may refer to as a crystal, or even as okay, just the active element. So there's going to be as okay a number of crystals for allotted to each transducer. It's probably not the number that is that important. It's more as okay the shape of the PCT that is going to as okay be an important factor. Mainly as okay to compare as okay over different resolutions. Okay. Now there's going to be as okay a mechanism of beam steering. How is it that your beam, as of course as okay produced by the XYZ number of crystals, is being steered in different directions. Another point would be the beam focusing. So what's going to be as okay the mechanism that enables yes okay the beam to focus at one or yes okay at multiple points. Along with this, okay, it means steering in different directions. Now we can mean it as okay, pretty much okay as very, it's okay, much related to yes okay the beam steering that will actually as okay indicate us okay as the image shape. Or the shape of the images produced by individual types of transducers. And last but not the least is going to be what is going to be as okay the consequence of yes okay damaged PCT effect on the image that we got, whatever shape it had. So how is a damaged PCT going to yes okay affect the image? Okay. Any questions? So for yes, okay, our list of our transducers, these are the 5 points that we'll be discussing for most of them. And that's where your questions are going to be coming from. Okay. Great. There are going to be, okay, some similarities, but there are going to be, okay, transducers which are going to be standing out or be, okay, different in their ways. Oh, yes, okay. Oh, yes, okay, effect of these 5 factors here. So, should we start with our first transducer? Get that one out of the way. So what was our first transducer?
Mechanical.
Mechanical, exactly. God, please don't do that. Yeah. Okay. Now, please, guys, this could also be referred to as a conventional transducer. Or as we will see, as okay, fixed focus transducer. So the first thing that we will talk about is going to be as okay, the number of crystals, or PCTs, or active elements that this transducer has. And that is very straightforward. It only got one single crystal. Is that clear? So no 2, no 3, no 4, just one single piece of crystal. Did you guys get that?
Yep.
Okay, just give me just 1 second, guys. Now, next is we say, yes, okay. Shape of the crystal. And here it's okay, the shape is going to be circular. Okay, let's circular. And if you want to look at it, just look at this. This is going to be the shape of your PCT for this transducer here. Okay. So what are these dimensions here? This will be the height. This will be the width. And then it's okay, this will be the thickness. Okay, now this is not a PCT, this is a quarter. Right, okay, but it's pretty much okay, a shape like a quarter. And this quarter has not been squeezed through, yes, okay, one of those things that they have at gas stations. Or yes, okay, or in amusement parks where you can get, okay, as a logo or something printed onto it. Okay, this is a regular round shape or circular shaped coin. Clear? Okay, so please keep in mind, guys, that this dimension here is equal to this dimension. Did that make sense? Okay, so when we made this, okay, say that it is round or circular, okay, it's going to be like this. Where we then in this case can say that, okay, yes, that this here is okay, was the width. Because it's okay, this width, we could say it's okay, was, let's say it's okay, for instance, 1 centimeter. Okay, well, okay, on the other hand, this was going to be the height. Okay, now the height is also going to be 1 centimeter. Did you guys get that?
Yeah.
Good. Now, guys, if we, for instance, says okay that we only had one PCT in the transducer. Okay. Now, guys, if this PCT mainly is okay was just here, and okay, as it was producing sound waves that will be able to just okay travel straight like this. That will mainly mean that okay, yes, your image or the shape of your image mainly as okay would just have been a straight box like this. Okay, and was pretty much okay as going to be of the same size. And in this case, if you could say that's okay, the width of your image, of your crystal or PCT. Okay, although that's okay, the beam could still focus, but you can still okay, you have this okay as one focal point here, for instance. Okay, so of one beam produced by this single PCT here. Okay. So our question is, because okay, what this transducer has okay still is going to produce a image which is not going to be like a box like this, but rather is going to be as okay what we will refer to as a sector shaped image. Okay, so this pizza slice shape image here actually is going to, it's okay, you hear that word again and again and again, it's going to be referred to as a sector shape. Okay. But had it not been for us being able to, yes, okay, steer the PCT, in this case, yes, okay, if we're not had been able to produce, or we will not have been able to produce this sector shape image. Okay, so the question is, okay, yes, only one PCT, how will that produce this? And that mainly is going to require that, okay, yes, the PCT, in this case, yes, okay, has to physically move this way and this way. So that's okay going to be a physical movement of the PCT here and here. Okay. Did that make sense? And as it moves, what is it that it's going to be doing? It's going to be be sending out beams. Okay, which actually you can say it's ultimately will form this sector shape image. So we can mean it says, okay, this part of the image here is mainly produced as the PCT physically move in this direction. Where we can say, okay, this part of the image here is mainly where the PCT is physically moved in this direction. Whereas, yes, this part here of the image is mainly produced when the PCT is in this direction. Is that clear? Now, mainly because in this instance here, it's that the PCT physically moves from side to side, just like a roller coaster or those pirate ships, bum, 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 or like a pendulum. Okay, that's why it's in this case we only say that, okay, yes, that the steering of the beam here is going to be mechanical. Because of, the mechanical or physical movement of the PCT itself. Yeah, okay. So just think of it this way. That, okay, yes, if this is the coin right now, it's sending out beam straight. But it moves like this, and it moves like this. Okay, so it's mainly just going to be sending our beams in the direction that it is moving. Did that make sense? Okay, so since there's a physical movement of the PCT, that's why we can say it's that the steering of the beam, which mainly means the direction in which the beam is going to be facing, is mechanical. Or if you just look at the term steering of the beam or beam steering, one is beam, right? Produced by your PCTs. What are the other words? Steering. What do you guys have in your cars?
Steering wheel.
Steering wheel. Okay, and what do you do?
Steer the car.
Steer the car. And how is that going to happen? The direction you turn the wheel in, the car is going to be heading in that direction, right? Did that make sense? Clear. Okay, so you want to go straight? Well, okay, yes, you have your steering wheel straight. You want to turn right, you go this way. You turn to left, you go this way. Clear. Okay. Now, this kind of transducers here, yes, okay. What they mainly said, okay, is that the V, yes, okay, the steering of the beam, which actually means that, okay, you physically, inside the transducer, physically move the single PCT around, okay? But mainly, yes, okay, had been controlled by a knob on the transducer. So for these transducers here is, okay, what could we say that we had? That, okay, yes. If we had a transducer, that transducer itself would have a knob, and which you mean, yes, okay, would just be twisting around. And okay, what that would do was mainly, yes, okay, going to move the PCT from one side to the other side. Made as okay by rotating the knob on top of the transducer. Did that make any sense? So here pretty much okay as turning or twisting on a knob on the transducer actually is okay would physically move the PCT because there was only one PCT in this direction and then dun, 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 like that. And by doing so, it's okay. In whichever direction, when it was over here, it was going to send beams here. When it, for instance, okay, here, it was some beams like this. When that single PCT was here, it was some beams like this. When this was over here, it was some beams like this. When it was here, it was some beams like this. When it was here, it was some beams like this. And when it was, for instance, here, it was some beam like this. Okay. And that is how, yes, okay, we went from, yes, okay, a single square or box shaped image to actually have an image which is going to be, yes, okay, like a regular image of most of our ultrasound transducers. Sector shaped. Or we can say, it's okay, fan out. Or have any of you ever seen a peacock? Spreading the feathers of its tail. What do you call that? It fans out. Or in the ancient times where we didn't have electric fans. Have any of you seen those handheld fans that you could, okay, I mean, yes, okay, that's cheap. But again, yes, okay, you could fold them together, right? Okay. But again, open them up and it's okay, use them as a fan. Okay. So that's mainly as okay where this whole thing is okay comes from. Okay. Any questions? but mainly because, okay, that there's, in this case, is okay, was a knob on the transducer itself that was going to cause by twisting it, was going to cause the single piece of PCT to physically is okay, go tick, 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 and yes, okay, sending out the beams in multiple directions as it was facing that way. And giving us this shaped image here, which was going to be as okay a sector shape or as okay a fan out shape image. Did you guys get that?
Yep.
Good. Any questions? Just like a lighthouse. Lighthouse only had one piece of light, right? Okay, or one light, or source of light. If that light was made, yes, okay, just facing in one direction. Right, okay. They will only see, yes, okay, what is right in front of it. To, yes, okay, to a certain distance. But what is the light in a lighthouse does? It moves back and forth like this, or from side to side. Yeah, okay, so you can actually say, okay, that was going to be the steering of the light source. Okay, but when it faces over here, it's mainly going to be as okay, throw light on what's over here. Where it goes here, they throw light here, and like that. Did that make sense? So that's the same concept that is being used here in this transducer. Now, guys, the next thing is okay, which is relevant to our, what do we call that? Beam. Was going to be, yes, okay, the focusing. Yeah. Now, what we said earlier, that in this case, yes, okay, this focusing of the beam was fixed. We also called it conventional focusing. And mainly, yes, okay, because this happens in a mechanical transducer, we call it mechanical transducer, we also call it mechanical focusing. Yeah, okay. Now, when we say that it is fixed, which mainly as okay means two things. One is fixed in the sense that can't be adjusted. Clear? Okay. That it can't be adjusted. That we can't move it to as okay a shallower depth or greater depth. And another factor of yes, okay, being fixed that is going to be as okay one single focal point. So in this image here, The remainder is okay, just had because it's okay, the PCT physically is okay, was moving from side to side. Okay. But where it says okay, fixed focusing. That's going to be as okay, we can say okay, focusing at a fixed depth. So let's say okay, as in this case is okay, that depth is at 1 centimeter, which mainly means that okay, as the beam is being steered, and okay, yes, they're going to be okay, beams being thrown out. These these individual beams, yes, okay, in this case, okay, we'll be focusing at one single focal depth, which was 1 centimeter, for instance. Okay, but it was fixed because we couldn't make it half a centimeter. We could not take it down to yes, okay, 1.5 centimeters or 2 centimeters or 3 centimeters or 4 centimeters or whatsoever. Did you guys get that? Okay, but so what we mainly mean by is a fixed focal point or focal depth here. It's not going to be as okay, it's only going to be as okay, focused at one point. But actually that's okay, but each beam as they travel, that's okay, they will reach its their narrowest point at the same depth throughout the image. Because we have one beam here, another beam here, another beam here, another beam here, another beam here, like this. But it's okay, they're all going to be focusing at the same depth in the image. Did you guys get that? But it was fixed in the sense that, okay, as we couldn't move it to a shallower depth. We cannot move that focal point to a deeper depth. Is that clear?
Yes.
Please, guys, and most students make this mistake. There's a difference between depth of image and focal depth. Just because you had a fixed focus transducer, okay, it doesn't mean that you can't increase the depth of your image. Did that make sense? Okay. So with this transducer here, it's okay. We say it's okay. It focuses at a depth of 1 centimeter. Okay. Let's say okay, we had set the image to begin with. That's okay. Just add 2 centimeters, for instance. But there's nothing that says that you can't increase the depth of your image to 3 centimeters, or 4 centimeters, or 5 centimeters, or 6 centimeters. Of course you can. But what you just have to keep in mind is that, okay, as the only depth at which you'll be able to focus is or fixed, which will be 1 centimeter. Just for an example. Okay, there may be transducers which has, okay, as focal points of that it's fixed, but it can be as okay at 1.5 centimeters. Okay, but what that means is, okay, yes, that you can't make it 1 centimeter or half a centimeter or 3/4 of a centimeter. Neither can you make that 2 centimeters, 3 centimeters, 4 centimeters also. That will be fixed. But yes, okay, along the entire spectrum of the image at a depth of, or at that fixed depth. Yeah, okay. So how is it that this transducer has these fixed focal points? How is that going to be determined? We already talked about that in the previous chapter. We says okay, it could either be as due to by mechanism of internal focusing. And what was internal focusing? That that the surface of the PCT was curved. Which mean overhead meant that is if this here was our point, one surface of the PCT would have a curvature. Okay, that would be internal focusing. So there's actually nothing new here. Okay, all something that we just talked about in our previous chapter when we talked focusing. You recall that? So it's just a matter of copy and paste. Okay. And that's why I say it's at that point, it's those were fixed focusing. Or we could have, or it could be due to external focusing. Okay, because both of these, were fixed focusing, right? Okay. Or conventional focusing or mechanical focusing. But what did it mean to have what was the mechanism, what was the mechanism of external focusing? Is that as we had a curved lens. And we can say in front of the PCT or crystal or active element. That we mainly could say it's that it would have been dependent upon the degree of curvature on the surface of the PCT that will determine the degree by which the sound waves that otherwise would have been traveling straight is going to refract. Okay, and the more they refract, the shallower is it that their focal point will be. Where, as for your external focusing, what did we have? Well, we had the regular PCT, but in front of that PCT was there going to be, curved lens. But again, it's going to be, the degree of curvature of that on the surface of the lens that will determine the degree by which, the beams will refract as they travel or hits that curved surface. And bring it to a shallower, deeper, or even deeper focal depth. But which after all was fixed because we couldn't change around with that. Why? Because that was pretty much determined by the build of the transducer itself. Did you guys get that? Okay, guys. Last point for this dude here is, okay. Okay. So what we had said was, this transducer here only got one PCT, right? Yeah, okay. It was going to be as okay, this PCT that would physically, as a result of okay, as being steered around, move from side to side, and was going to be steering and because that's okay, send out beams. And when that's okay, all dependent upon that's okay, the size of the PCT or the mechanism, that's okay, would because that's okay, reach to a fixed focal point depth throughout that's okay, the sector shaped image. Did you guys get that? Now the question arises, because okay, as what is that the sound or what was it that this strand of PCT was doing? It was sending out energy. Sound waves that will reflect back and okay, yes, ultimately is okay, produce as okay the image that we see on our screen, which in this case is going to be as okay shaped like a pizza slice. Yeah, okay. But this was only possible because okay, this PCT here is okay, was physically working. If this PCT here is okay gets damaged due to whatever. Yeah, okay. Now, although yes, okay, it may move this way, and or yes, okay, it may move this way. But since that's okay, the PCT is damaged. What's going to happen? Well, okay, no sound waves will be transmitted. Likewise, even I read here. And likewise, even if it moves over here, it's okay, no sound waves will be transmitted. So forget about it focusing on things like that. No sound waves will be transmitted, hence no sound waves will be reflected either. Yeah, okay. And if sound waves are not being transmitted and not being reflected, what is it going to be? That okay, as our system is not going to as okay receive any energy in whatever form that it will be able to transform into an image. So you have a complete blackout. Did you guys get that? Okay. Just think of it in this way as okay, we only got one source of light and we turn that out. What do you have? A complete blackout, right? So the same here. So that's okay, you will have no image if there is a damage to the PCT, because there was only one PCT in this transducer here, right? If the light in the lighthouse bing, that's okay, goes off, what's going to happen? Would that lighthouse be able to, yes, okay, throw a beam of light? The bulb may be moving from side to side. That's not the question here, but it's okay if it doesn't throw out any light. Would you be able to see what's over here or here or here or here? No, right? So that was your mechanical transducer. Okay, so it's going to be mechanical, mainly because, okay, its focusing is mechanical. In the sense that, okay, what's the mechanics behind either external focusing or internal focusing? Okay, the steering is mechanical. Okay, okay. Or more actually, it's okay, you can say it's okay, more manual, because here in this case, okay, the actually circuit was a knob on top of the transducer, which has to be manually rotated to, yes, okay, physically move the PCT so that it could send out beams in multiple directions. And each of those beams would focus at a fixed depth. Right? But that doesn't mean that you can't increase the depth of your image. If your focal depth was 1 centimeter, yes, okay, you can increase the depth of your image to 2 centimeters, 3 centimeters, 5 centimeters, 10 centimeters. Nobody will forbid you for doing so, or it's not going to be as okay. So those two things are two different things: focal depth and depth of image. Yeah. Okay. Just keep one thing in mind that, okay, yes, if your focal depth is 2 centimeters and you keep the depth of image 1 centimeter, then you won't reach the focal point. Okay. But just because your focal depth was 1 centimeter doesn't tell it's not going to be as okay. Forbidden to, as okay, increase the depth to 2 centimeters, 3 centimeters, 5 centimeters, 10 centimeters. So those are two different things. Clear? Depth of image and focal depth are two different things. Just think of it. You may be standing out as okay on a nice sunny day. The sun is shining. Looking at a plain field. And you actually be able to look up to just okay, a distance of like 5 miles. Because there's no clouds, no fog, nothing. Okay, so here is okay, your depth of field or depth of view or depth of images, 5 miles. Okay, but in that area of 5 miles ahead of you, it's okay, there may be a point on which you focus. You may say, okay, there's a little child running in those fields, playing, or it's okay, running a kite or something like that. That catches your attention. That's going to be your focus. Did that make sense? Okay. Well, okay, if your visibility only was 20 feet and that child was playing at a distance of 3 miles, you won't be able to see him or see her because of a low visibility. Did that make sense? But here what we mean is, okay, just mean by is, okay, a fixed focus is, okay, as that can't be adjusted. Well, you can adjust the depth of your image as long as it's more than the focal point or the focal depth. Okay. Well, that's why we say it's okay. Focal depth is going to be, it's okay, the depth. Okay. Not just as okay, one point. Well, it's okay at this fixed depth here. That's okay. Throughout, from side to side, from side to side of your image. Which means will be that, okay, yes, this is the point at which, or this is going to be as okay, the single depth at which is okay, each beam, when it is okay, being thrown out, is going to, it's okay, reach to its narrowest point. Any question, ladies and the gentlemen?
No.
No. It's okay, guys. Just take a short break, and when we come back, it's okay. We will talk a bit about it's okay, our annular array. Okay. So yes, okay. Let's see. 3 small pages that you guys can read on, and then we're going to just okay take a step and go on to page 178 when we come back. So I see you guys, and should we say at 10:45? Read on your annular. I'd read on not your annular, sorry, on the mechanical transducer as well. Okay, guys. Okay, guys. Sorry. Um, any questions regarding your mechanical transducer? Nope. Okay, guys. So yes, okay, we can just go to page 178. And what we will be talking about here is going to be, yes, okay, the annular phased arrays. Now, guys, once we're done with this, just okay, you will realize why I chose this one here first. But let's just get one thing clear is okay, that whenever you see the word array, it's okay, referring to a transducer. That will mainly mean that it will have multiple focal points. And what do you mean by multiple focal points? Because it's okay, can focus at multiple depths. What can focus at multiple depths? The beam. Is that clear? So whenever you see the word array, that will mainly is okay. We reference to that, okay, we have multiple focal points in this image, or we can produce multiple focal points. Just because you can do something, that doesn't necessarily mean that you have to. Okay, guys? Okay. Even as okay, using multifocal transducers, or as okay, array transducers, you still may just want to focus at one point or one fixed depth. Now, our first point here is going to be as okay, the shape of PCC. Now here, guys, is okay, the shape of the PCT is going to be, let's do this guy. Round. Or as we can say, it's okay, circular. If that makes sense. So we can say, it's okay, this was our PCC, yes, okay, these are going to be the width and the height. But what we then also will see is that, okay, yes, we have this PCT here. Which means, okay, look at that by itself is going to be disc shaped. And this is going to be as okay, your PCT just with okay as the empty space here. Why? Because that was going to just okay fit this circular PCT. We can just okay say we have another piece of PCT as well, which also is going to be as okay disc shape because it's like this. So if you took that separately as okay by itself, say it's okay. This was going to be your PCT. Okay. Just for sake of fun, we can say it's okay. We may even have here's another PCT, which also will be disk shaped. Guys, okay, if we took that separately, it's okay. This will be it. Okay, we mean because it's okay. These two pieces of PCTs will fit in this space here. These three PCTs, all yes, okay, will fit in this space here. Okay, but where we still see whether yes, okay, where there are circular or disc-shaped PCTs, that okay, yes. This would be the width. This would be the width. This would be the width, which is going to be as okay, or which was going to be as okay, the same as the height for each individual PCT. So in each of these PCTs here, we can say that the width and the height was the same. Likewise, for this one, it's okay, it will have the same height as its width. Like right here, it's okay, we'll have the same width as the height. Same over here, it's okay, it will have the same width as its height. Which may mean that, okay, yes, if this here is okay, for instance, okay, was half a centimeter, then this will also have to be half a centimeter. If this here is okay, the width of this here was 1 centimeter, then the height will also be 1 centimeter. Yeah, okay. Whereas, okay, because if this width was okay 1.5 centimeter, then the height will also be is okay 1.5 centimeter. And so, like here is okay 2 centimeters, for instance, is okay. Then this will also be 2 centimeters. You guys get that? Okay. But practically, yes, okay, although that's not how it's mentioned in the book, but we can make this as okay, it's only going to be the central one. This one here, which will be round or circular. The remaining, yes, okay, will just be disc shaped because, yes, okay, why I call these disc shape here because they are, yes, okay, shaped like a CD or a DVD. In both cases, okay, the word last D here is okay, stands for disc. Okay. Did that make sense? Now you may have to dig into your old digital library, okay, of movies or whatsoever to see as okay what a CD or a DVD looks like. Did you guys get that? Okay. But we can mainly say that okay, yes, the smaller piece of PCT fits into the bigger, where these fits into the bigger, where these all fits into the bigger. Okay. Now please, okay, as although yes, okay, in your book, you only see yes, okay, 4 crystals or 4 PCTs given. And I just drew 4 PCT here. That doesn't mean that it's okay that there's going to be a standard of 4 crystals in an annular array transducer. That can be 5, that can be 8, that can be 10. Clear? Okay. Okay. Did that make sense? Okay. So here's okay. Now really we can say okay, we're not going to be bothering much about is okay the number of the PCT, but it's actually it's okay just going to be the shapes of the PCTs that are of importance. Okay. And one thing to take away from this here is that the width of the crystals, that the width of your crystals equals the height of your crystals, just as it did in our mechanical transducer, because it was shaped like a coin. Okay, and this one here we can make this okay, just say it's okay, we have coins of different shapes or sizes. Did that make sense? Where the smaller coins made this okay, just fits into the bigger coins, which just fits into the bigger coins, which just fits into the bigger coins. Okay, but all these PCTs, yes, okay, of different dimensions. Okay, where we can say yes, okay. Please don't do that. Okay, when we look at it, this one here is the smallest. Then we have something which is okay, yes, bigger. This is going to be even bigger, and this is going to be yes, okay. We can say it's okay, the biggest. But the smallest fits into the bigger, which fits into the even bigger, which fits into the even bigger. And mainly as okay makes that all these PCTs here is okay, tuck, 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 makes yes, okay, one big unit of, or we can say yes, okay, multiple PCTs just fitting into one another. Did you guys get that?
Yep.
Right, okay. Okay. So just like your mechanical transducer, in this case, it's okay, all your PCT becomes just okay, one big single body. But actually, that's okay, made up of multiple crystals. That's where it's going to differ from your mechanical transducer, because in mechanical transducer, there was only one crystal. Did you guys get that? Now, guys, comes the question. How is it that this, we can say it's okay, bigger group of PCTs is going to be steered? Mainly because it's okay, we have okay, yes, this was just okay, the whole body of our PCTs. Clear, okay. So which makes us okay, a big chunk of PCTs or crystals. And again, guys, it is mainly as okay, physically going to, yes, okay, just like in a mechanical transducer, physically, yes, okay, being moving from side to side. So where we can say, yes, okay, that, okay, yes, when it was here, it was going to, yes, okay, throw out beams in this direction. Whereas, okay, yes, when, for instance, okay, here, they were going to, yes, okay, throw beams out in this direction. Like, okay, yes, when they were here, or when it was here, yes, okay, I was going to throw a beam in this direction. And when, for instance, okay, they were here, they were going to throw our beams in this direction. And last but not least, it's okay, when they, for instance, okay, here, we're going to throw our beams in this direction. Okay, but here, yes, okay, so yes, okay, we can mainly say it's okay because the PCTs, yes, okay, as a chunk or as a group together, is going to just, okay, physically move like this. And this way is okay. We mainly say it's okay that that was going to be, it's okay that our steering of the beam is still mechanical. Yeah, okay. But what they did here was that, okay, yes, that there was not necessarily going to be, as okay, a knob on the surface of the transducer. They got rid of that, but mainly says, okay, that there was an inbuilt motor in the transducer, which was mainly as okay, where the motor here actually is okay, was going to be responsible for the back and forth movement of the group of PCTs. Did you guys get that? But the steering of your beam is mainly still going to be mechanical. Okay, but we can say, okay, mechanical is okay by help of a motor. Okay, just the same that, okay, as what we use the knob for in the regular mechanical transducers. Okay, which means, okay, we're going to call steered, as I said it, steered the PCTs as okay from side to side. And by doing so, it's okay, that actually led to that the beam would be steered in different directions. Did you guys get that?
Yeah, so this one just has the motor inside and the other one
Exactly.
has. Okay.
Exactly. Yeah, and then your mechanical, yes, okay, there was just going to be a knob. Okay, dear? Okay.
Yep.
But you can say it's okay, mechanical in the sense that, okay, yes, the PCTs still had to move from side to side. Yeah, okay. And whichever is okay direction that it was facing in, what was it going to do? Throw our beams. Did that make any sense at all? Yeah,
Yep.
okay. Good. So since it does that, yes, okay, we may say, okay. This might have been, yes, okay, your transducer. We can say, okay, the group of PCTs may move this way and that way. And that causes that, okay, yes, you still get this sector-shaped image. Did that make sense?
Yep.
Good. Now, guys, one thing about, yes, okay, the sector-shaped image, let's just look at it. So you can say it's okay. This here is okay, what's your transducer? Now this is what we mean, yes, okay, we'll end up calling, yes, okay, the footprint of the transducer. Clear, okay. Now what's going to happen in, okay, as a sector-shaped image? Or what we say is, okay, will be as, okay, a sector-shaped image. It's going to be like this. For instance, let's say that, okay, here's, okay, we have a depth of image of 5 centimeters. Okay. The footprint of our transducer may just be, let's say, it's okay, 2 centimeters, for instance. Did you guys get that? So what do you see here in the sector shape image that, okay, guys, the deeper we go, the side-to-side dimension of the image may cover greater distances because it's okay, guys, if we go to, for instance, okay, a depth of, let's say, 10 centimeters. This is a depth of 10 centimeters. Okay. Although it's okay, your transducer was only as okay, had only a footprint, a surface area that came in contact with skin, which was 2 centimeters. That's what we mean by the footprint. Okay. The part of the transducer that comes in contact with the skin. Which only was 2 centimeters, but what we can say is okay, will be as okay, the width of the image here might have been 3 centimeters here, might get up to as okay, 4 centimeters here, maybe as okay, 5 centimeters wide here, maybe as okay, 7 centimeters wide here, maybe 10 centimeters wide, and so on, so here, maybe it's okay, 15 centimeters wide here. Let's say it's okay, 18 centimeters wide. So what do you see in a sector shape image? That the deeper and deeper and deeper and deeper and deeper you go, the area that's being scanned compared to as okay, the footprint of the transducer is greater, right? right?
Yes.
Any questions? Okay, so you may not get a physical shape, or that's okay, an actual a shape of an image demonstrated on the question, but they may verbally explain it. So how can you explain as okay, verbally explain as okay, a sector shape image? That it becomes wider and wider as you go deeper and deeper, right? Yeah, okay. Or where you can say it's okay that the footprint doesn't match the width of the image at different depths. Mainly because okay, the image gets wider and wider. Okay, guys. Any questions? So this was your sector shape image. Now in this tool here. Now the next thing that will come across is going to be is okay, what about the beam focusing? Now as we said, we had multiple PCTs. We're just going to stay with 4. That makes sense? So we says, okay, we had a small PCT, which fitted into, yes, okay, a bigger PCT, which fits into a bigger PCT, which fits into a bigger PCT. But what we mainly can say is that these dimensions for the smallest PCT or the central PCT is lesser than these dimensions of the bigger PCT, which is lesser than these dimensions of the greater PCT, which is lesser than these dimensions of the biggest PCT. Okay, and what do we mean by beam focusing? It's going to mean that's okay, just going to determine at what depth does the beams, because each of these here is okay, were individual pieces or PCTs. So this PCT will produce its own beam. This PCT will produce its own beam. This PCT will produce its own beam. And this PCT will produce its own beam. But where is it that, or what depth is it that these beams of each of these PCGs here, yes, okay, will focus at? Or what do we mean by yes, okay, beam and focus at? Mainly yes, okay, means that they get to their narrowest diameter. Right? And that will mainly as okay, just be the focal depth for each of these individual PCTs or crystals. Now, guys, if you remember back in a previous chapter, we said that focal depth was directly proportional to diameter. Well, okay, that's what the book said. But where I say, okay, diameter or what? And I elaborated that by saying it's okay, the diameter of the PCT. Did you guys get that? So yes, okay, guys, if we look at the image produced by our transducer here, where mainly says, okay, this part here is going to, yes, okay, or this portion of the image is mainly going to be, yes, okay, when the PCTs are over here. We can say, yes, okay, this portion here is mainly as okay when the PCTs or that's okay, the growth of the PCTs are here. And we can say it's okay. This part here of the image is mainly is okay produced when the PCTs were steered over here. But together with that is okay. Each of these PCT here was going to is okay through our beams. Which then, although yes, okay, it was one big body of multiple PCTs, but they would be focusing at increasingly greater and greater depths. Did that make sense? Which mainly or mean that, okay, yes, when the PC, yes, okay, when the group of the PCTs were moving tick, 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 like this, the red PCT mainly is okay, we were focusing at these fixed depths here. This pale green, light green, or whatever you want to call it, would be focusing at these depths, or at this depth, because it has a greater diameter. The light blue one, or the blue one, or sky blue one, will be focusing at this depth. And okay, yes, this brown one here, okay, meaning because that was the biggest, we'll be focusing at this depth. As the PCT or the groups of PCTs, that's okay, will move from here to here to here to here. So when it was here, each of these would function as okay, focus at their own depths. And it was here as okay, will focus, each of them will focus at the own depths. Each will focus at the own depths, each will focus at the own depths. Okay, where the concept mainly as okay was the smallest piece of PCT, which was going to be the central, would focus at a shallow depth. Or we can say it's okay, lowest focal depth, because that was the smallest PCT in terms of diameter. Whereas, okay, yes, this would be at a greater depth because of a greater diameter. The blue one would be at a greater depth, or even greater focal depth because of a greater diameter. And the last but not the least, greatest because of the greatest diameter. Did you guys get that? So yes, okay, your annular array transducer. Although yes, okay, the PCTs as a big chunk were mechanically steered, but because that big chunk of PCTs were made up of PCTs of different diameters, each of those had their own focal depth. Or what we mainly can say, guys, is that the small PCT, this fellow here, mainly as okay will make this part of the image. Where we can say it's okay, this greater PCT here, mainly as okay, we just make up this part of the image. Whereas okay, as this PCT mainly is okay, will make this part of the image. And it's okay. Okay, please. Yeah, this PCT mainly is okay, will make this part of the image. But then the mainly is okay, just going to be brought together. Did you guys get that?
Yes.
So although yes, okay, it was one big body, although it's okay, made up of multiple crystals, smaller fits into bigger fits into bigger fits into bigger fits into bigger fits. And although yes, okay, it was mechanically steered, mainly because okay, this big body of multiple PCTs were thrown in one direction, another direction, tick, 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 back and forth, back and forth. But due to yes, okay, the difference, or yes, okay, the different sizes of each of the individual PCT, they were able to focus at different depths, because focal depth in this instance here is okay, was directly proportional to the diameter of the PCT. Did you guys get that? Any questions? Nobody want to say anything?
Not yet.
Not even an okay. Okay. So again, yes, okay, guys. The shape of the image is sector shape, fan shape. We talked about that earlier. Doesn't mean it's okay, but okay. Just like the mechanical transducer, yes, okay, here the back and forth physical, yes, okay, steering of the chunk of PCTs. Now, guys, what I just said earlier was, okay, yes, if this here is okay, was our image, where we say that, okay, yes, this depth here of the PCTs, or this depth here of the image was mean, yes, okay, by the small PCTs, where we could say, yes, okay, this depth here of our image was mean, yes, okay, due to this bigger PCT. Where we could say, yes, okay, this depth of our image here is okay, mean, yes, okay, was due to this PCT. And last but not the least, yes, okay, here, this depth of our image was mean, yes, okay, by this PCT. Now our question is going to be, yes, okay, guys. Okay. And please keep that, okay, yes, at that, okay, yes, as the PCT is steered like this, and is steered like this, yes, okay, that may cause that, okay, yes, we're going to do this. So, okay, this side, you can see it's okay here. It's here, it's okay, it's going to be this part of the image. And if we see it's okay over here, it's going to be it's okay. This part of the image. But let's just say that, okay, yes, guys, in this case, yes, okay, we say that one PCT is damaged. And okay, what would be a better idea than to damage the blue one? So blue one here is damaged. Did you guys get that? Now, what would that mean? The added depth that was scanned or focused by the blue PCT. No signal will go to this depth. Come back. So saying yes, okay, nothing is being transmitted, nothing being reflected by this PCG because it is damaged. That's why yes, okay, we actually yes, okay, will have a horizontal defect. So yes, okay, our image is going to yes, okay, mean yes, okay, be something like that. We'll get from the red. Yes, okay, we'll get from yes, okay, from the green because there's nothing wrong with that. We stay yes, okay, get let's say yes, okay, info from the brown. But it's okay, the one area is okay that we are not going to get anything from is the area that was scanned by the blue PCC because in this case, it's okay, that was the one that we said that was damaged. Okay, okay, yes. As it moves along, yes, okay, from side to side with the other with other pieces of crystals, red in the center, green, and okay, the brown around it. Okay, but this depth here is okay. Whether it was still in this direction, well, okay, no signal from this area here. Oh, that's okay, whether it was still in this direction, so it's okay, no signals from this area over here. Or whether it was on the center, it's okay, no signals from this area here. Did that make sense? Because that side to side actually, which okay, it was okay as a sector shape image was due to the steering of the beam. Which in this case, as I mean, it was okay at that back and forth. Ding, 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 motion of the of your PCG. So here you can see as okay, if you are looking at a horizon, and say, well, okay, I can see anything from the first meter to the for the first 10 meters. But from 10 to 12 meters, I'm blind. And from 12 to 20 meters or whatever is beyond that, that's okay, I can see. So what will you be? Okay, you'll be blind in that area there, okay, which means you can say, okay, your vision is damaged to focus at those depths, at that distance. Okay, so whether you look straight, whether you look this way, or whether you look that way, in the entire spectrum is okay, you will be blind for that distance, 10 to 12 meters. Anything that is at a distance of 12 to 12 meters, no matter is okay, whether you look this way, this way, this way, this way, this way, you won't be able to see. So on your image, that's okay, that's going to be as okay across your image. Okay, or as we said, that okay, guys, please. If we say that okay, yes, we focus at 5 centimeters, for instance. Okay, that's going to be as okay that we focus at a depth of 5 centimeters. Here, 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 all across. Or we may say it's okay that we focus at a depth of 10 centimeters. But that mainly mean that okay, yes, across the entire spectrum of the image. Is it that okay, whatever beams we send out, that's okay, they will focus at this depth here. Did you guys get that? So here, what do we get? A horizontal. effect across the image at the focal depth. That was your annular array transducer. So some parts of it was pretty similar to your mechanical transducer, especially as when we talk about the steering. Okay. But what actually is enable this transducer here to be able to focus at more than one focal point, which makes it an array transducer, versus your mechanical transducer, which only had one focal point, was that this fellow here had multiple PCTs, smaller fitted into the bigger, fitted into the bigger, fitted into the bigger. Did you guys get that? Okay. So a munchkin fit into, yes, a donut. That donut fitted into a bigger donut with a bigger hole. Fitted into a bigger donut with an even bigger hole. And so on. Did that make sense? Okay, guys. Any other questions? Or do I need to clarify this more? Nope. Okay. So takeaway point is focal depth equals or yes, is directly proportional to the diameter. Okay. But the shape of, guys, because this shape is going to come and bite you in the, that's okay. May not be a perfect circle, but that's okay. When you see a circular, that's okay. This dimension here, a length, is still going to be equal to this length here. Clear? Okay. Yeah, guys. What will this determine? The width of the beam. And what this fellow here will determine is going to be the height of the beam. Which of course is going to narrow down at the focus. Or even then, US at the focus, this is still going to be equal to this in terms of measurement. Capiche? Because what did we say that a beam was? Had an hourglass appearance. Okay, but how did I get that? Mainly because the side-to-side conversion was equal to the degree of top to bottom the conversion. Okay. So you is at the focus, yes, the height of the beam will be equal to the width of the beam. When we have circular around or US, okay, disc-shaped PCTs. Okay, guys. Now, when we come back after your lunch or brunch or crunch, whatever you call it. Okay. What I will do, okay, yes. We can go as, okay, some generalized concept for the remaining of our array transducers. Okay. Some generalized concept which we made as, okay, will just be as, okay, copying and pasting. Okay, guys? Good. So should we say that I see you guys at 12:50? You can have your lunch. Please read on your annular array. Okay, guys? Please read on your annular array as well. Okay? So I see you guys at 12:50. Have fun today. Welcome back. And Zinga. Any questions?
Not yet.
Not yet. Hey guys. So let's just do something, and we can say we talk about what we can call this, okay, array transducers. And what did we mean by array? Multifocal or adjustable focal points. Okay. Now, one array transducer that we already have talked about is the annular phased array. Now, just a few points is what we had was circular and disc-shaped PCTs. The steering is mechanical. And we can say, okay, the focusing of beam is based on diameter of PCT being directly proportional to focal depth. Okay, so mainly as okay as we see here, that's going to be one of the things that we as okay will have to find an alternative view for. Is that okay as the steering of the beam was mechanical. Okay. That is going to be different from for our next set of array transducers, which mainly can say is okay, now the other set of our array transducers are going to be okay, what we can call linear phased array. But the array still means it's okay that this is going to be as okay, having multiple focal points, and or that the focal points could be adjustable. Another kind of array transducer is going to be as okay, what we'll call a linear sequential array. Another kind of array transducer is going to be curved. It can also be called a convex, and or it can also be called a curvilinear. And of course, SOK is going to be SOK an array transducer. Yeah, okay. That all these cases here is okay. What did the term array stand for? That okay, as they were able to focus at multiple points. Is that clear? Now, what we also see is okay in these names of the name of these transducer here is the common term linear. Okay. Now the term linear is okay, mainly can be taken as okay in two ways. What's going to be common when we talk about these two, the linear phased array and the linear sequential array, is that they pretty much okay have a straight linear footprint. That we mainly can say as okay that the reason that we call linear, it could be that they have a straight linear footprint. Okay, which is going to be as okay a little bit off in this one here because the footprint in this one here is going to be curved. That's why it's okay we call it as okay a curved or convex, or it's okay even curvilinear. Okay. But what we mainly can say that okay, as all these three transducers they have in common is that if we look at the PCTs, or crystals as we may call them, is that okay, yes, that the PCTs are lined up. You can say, okay, side by side. Or just like, okay, yes, if you look at it in this way. Lined up like soldiers standing guard. which mainly means, yes, okay, that they will be standing shoulder to shoulder. Did that make sense? Okay. So yes, okay, as far as okay, your linear convey as okay, sorry, your linear phased array, and or yes, okay, your linear sequential array is concerned. They could be called linear mainly because they had a footprint which was okay in a straight line. Okay. But those two together with your curvilinear, and again, yes, okay, the word linear comes with the term curvy because okay, its footprint is curved, but even in that, yes, okay, the PCTs are going to be lined up side by side or shoulder to shoulder. Clear? Okay. You guys or anybody, not just you, anybody, yes, okay, can be standing shoulder to shoulder along a straight line. Likewise, anybody, yes, okay, can be standing shoulder to shoulder and okay, still be making a curve like this. So most likely, yes, okay, what we will say that, okay, yes, that the word linear, and linear occurs in the names is mainly because that, okay, yes, the multiple PCTs that we have in these transducers here are going to be lined up side by side. Did you guys get that? Okay. But let's just say that, okay, yes, we were PCTs lined up shoulder by shoulder next to one another or side by side. And we were producing a beam until and unless directed otherwise, you would have been looking straight ahead, right? Did that make sense? So whatever sound wave the transducer would produce would be facing straight ahead. So if you said, okay, yes, if this, for instance, okay, was our transducer here, it could have been this or this here, for instance, which would be this. And these were our, sorry, PCTs. When they fire, they would just have been firing straight ahead. Or whether it was our curved transducer, when these PCTs, yes, okay, which were lined up shoulder by shoulder like this, or side by side, when they fired, they would just have fired straight like this. Where you mean because says, okay, if that was the case, then okay, yes, that would mean it had been because there had been no steering of the beam. Okay. So guys, what all these transducers here are going to have, all of them, even as okay, the one which is not mentioned here, but that's mainly because okay, it's not actually a linear, it should be a vector array. Okay. But what all these transducers here will have is going to be as okay, what we will call a channel. not channel, sorry, channel, sorry. Okay, guys. Now the question just is, okay, yes, what makes up a channel? Now your channel is mainly going to be made up of a PCT. Which is going to be connected via a wire. Just to make it clear, guys, okay, as this wire is going to be as okay an electrical wire to an electrical source. Did you guys get that? So this combination of these three components here makes up, that's okay, what you call a channel. So if a transducer, for instance, had, that's okay, we can say 250 pieces of PCTs or crystals lined up, side by side. What would that mean? That each of these PCT will have their own electrical wire that is attached to, yes, okay, some electronics in the system. Did you guys get that? But this whole thing here, even if you just take one electrical source with a single wire and a PCT, makes one channel. So in this case, here we can mean it says, okay, this transducer, maybe because of the 250 PCTs, for instance, okay, how would have had 250 channels. Did you guys get that?
Yes.
Okay. So guys, it is mainly going to be as okay, we can say as okay, let's say, let's do it this way. The sequence in which the PCTs will produce sound. That sequence in which the PCT will produce sound that is going to determine whether our beam will be steering this way, whether our beam will be steering this way, and or whether the beam will be steering this way. And or, because this is going to make us, okay, be what most of these transducers here will do. Because it's okay, may start from this pattern that all the PCTs will start firing this way just okay as switching over to yes, okay, firing this way. And then ultimately as okay, start firing this way. So what we now is okay, mechanically steered transducer head was that okay, the PCT physically moved. That's not going to be the part. That's not going to be possible here. All dependent upon whether I'm the first, followed by us, okay, the fellow standing here, followed by the fellow standing there, so on, so on, so on. Then we go in this way, will determine whether yes, okay, my beam will be facing, or whether we will be steering the beam in this direction, or in this direction, or straight ahead. Did that make sense? Now, where is all that going to be controlled from? The electrical source. So that's why we mainly as okay will end up saying that the steering in these array transducers here is going to be electronic. Or as I said in the previous chapter, when we talked about focusing and saying array focusing, which we mainly as okay, just simplify by saying multiple focal points. Okay, but we said there was electronic. Okay, did you guys get that? Okay, but even yes, okay, the steering of the beam in this case as well is going to be electronic. So if you were standing, yes, okay, side by side, shoulder to shoulder, what would determine whether the beam was going to be steering this way, this way, this way, this way, this way, this way, was mainly as okay controlled by the electronics of the system that produces the signals, send it down to the wires, which stimulates your PCT that produces the sound that would be steered in multiple directions. So the sequence all depended upon that we can say is okay. That's shit, sorry. That if this PCT here is okay was the first, and this PCT here is okay was the last. Now many cause that okay, yes, the beam will be steered in this direction. Whereas if it was the other way around, that this PCT was the first, and this PCT here is okay was the last, then our beam will be steered in this direction here. Okay. And when they not super exactly at the same time, but it's okay, pretty much closely as okay, fire at the same time as okay, your beam will be steering straight. Okay. But as okay, we can mainly say okay, it may as okay start from this pattern, that this PCT first, this fires last, going on just okay, firing at the same time, and then okay, going on to that this become the first and this become the last, and cause the beam being steered in this direction. So instead of physically moving, okay, physically yes, okay, moving off the PCT or group of PCTs, is me as okay, just well, okay, we are standing. You all get the command, look right, look straight, look left. Did that make sense? Okay. Okay. So where's that command going to come from? The electronic source. So for all that's okay, our transducer that we will be talking about is that their steering is electronic. What determines that? The sequence of the PCTs being stimulated. Okay. Very main is that's okay. This PCT was first. This was going to be the last. Then beam was steered in this direction. Whereas if you went the other way and say, yes, okay, this PCT here was first, this one here was last, then okay, yes, the beam will be steering in this direction. And when the fire close to the same time, they have a call that okay, yes, the beam will be steering straight. But yes, okay, it goes, for instance, blue, then it go yellow, and then it go pink. And that's how it's okay, your beam goes this way. Then it goes this way, and then it goes this way. And that's how it's okay, you get this image here. For most of our transducers. Did you guys get that? So that's why I say it's okay, the sequence in which the PCTs are stimulated or produce sound wave, that is going to is okay determine the direction in which the beam is steered. Did you guys get that?
Yes.
Yep. Now just another point, guys. And again, we can say it's okay, we have the transducer. We can say it's okay that we have the XYZ number of PCTs, which are physically as okay lined up side by side to one another. Right? The next thing is going to be, which mainly as okay again will determine, because physically yes okay, size wise that's okay, each of these PCTs yes okay, the PCTs yes okay have a specific well okay shape. We'll talk more about those yes okay tomorrow. Okay. But it's okay, they have a shape, and the shape of all of the PCTs are the same. Okay. Had this been yes okay, like in a mechanical transducer, that would still have caused that okay, yes, they would have been all just focused at one single focal point. But that is not going to be the case. Because, okay, what we were able to just, okay, do with these transducer here is choose it to just, okay, focus at, let's say, it's okay, one point or another point. Where we can say, it's okay, this will just be as okay, or shallow focal point. But we can also choose it to, yes, okay, pretty much okay, at the same time, yes, okay, focus at a deep focal point. Did you guys get that? And please keep in mind, guys, this still happens just okay as the beam steers. Or at the same time as the beam is steering. Did that make sense? But, the factor that is going to, yes, okay, determine the focal depth of the beam obviously going to, yes, okay, determine the focusing of the beam. In this case, here is going to be something that we'll call a phased delay. Did you guys get that? So what in the is it that this phased delay is? Now, guys, as we said earlier, we might have said, okay, as this was the first PCC true, fire, this was the last. Right? Yeah, okay. What did that cause? Rikume says, okay, Dawame says, okay, make the beam says, okay, be steering in this direction here. Okay. Now, since we say this is first, this is last, that will mainly mean that, okay, yes, this is followed by this, which is followed by this, which is followed by this, which is followed by this, as we go on. Okay, so that sequence with this being the first, and means like the domino effect, this being the last, cause the beam to be steering in this direction here. But as we, yes, okay, say, let's okay that the beam, yes, okay, here has been steering in this direction. We still wanted to, yes, okay, focus at this depth here. Let's say, yes, okay, 2 centimeters, and we also still wanted to focus at this depth here. Let's say, yes, okay, 3 centimeters. Because that was mainly, yes, okay, what we did when we increased our focus number. Did that make sense? That we says, okay, don't just focus at one point, but actually, it's okay, focus at 2 points. And then we just, okay, set that as those respective depths or positions. So these were just okay, just the two different positions of our focus that we did by SOK, because SOK adjusting the focal pause on our system. Yep. Okay. And what that is going to do is mainly SOK going to SOK causing these PCTs, yes, okay, to firing off with different phase delays. So what we mainly as okay will say that for a shallow focus, when we focus at a depth of 2 centimeters, we will have okay as a great phase delay. There's going to be a great phase delay. Whereas on the other side is okay when we focus at a great depth. This case is okay 3 centimeters. There's going to be a lesser phase delay. And what in the is it that this phase delay is? Well, okay, it lies in the word delay. Now, what does the word delay mean?
Like a pause.
Pause, or we can say it's okay, the time interval, right? Okay. Okay. If we play, yes, okay, brainstorm, tsunami jeopardy. Right, okay. What could we say? Well, okay, yes. The delay time between the question being asked and the answer will be as okay 5 seconds. So you can only as okay delay the answer for 5 seconds. If the delay is more than that, bam, the buzzer is going to sound. Did that make sense? Okay, so what is going to be the phase delay here? It's mainly going to be, guys, the delay between firing of this PCT to this to this to this. So what they mainly say is that for a shallow focal point, or if we want to focus at a shallow point, we say, okay, the beam is being steered in this direction here. Okay. But saying, yes, okay, we focus at a shallow point, that's when there's going to be, as okay, a great phase delay, which mainly will mean that, okay, as there will be a greater interval between firing of this PCT to the neighboring PCT. So we can say, okay, this phase delay means, okay, just the interval between the, okay, I may use the word firing, but you can mean, okay, say a stimulation or so on, so on, so of neighboring PCTs or crystals. That's pretty much okay as what the phase delay would be. Did you guys get that? Now you may say, well, okay, now since yes, okay, in this case, yes, okay, we had set the transducer to focus at 2 points or at 2 depths. one has to come first, followed by the next. And guys, the way that it mainly is okay, will work that okay as if a transducer or if a system is being asked to focus at 2 points. You can go to 3 points, you can go to 4 points, you can go to 5 points. That's not the, okay. But what it mainly is okay will take care of is going to first, it will focus on the shallow depth. Then, followed by deep. You can see it's okay if we even had okay as a deeper focal point. Then the deeper. And so on. So first, shallow focal points will be taken care of. Then the deeper, then the deeper, then the deeper, then the deeper, then the deeper. Okay. But guys, this just happens so rapidly. That the picture that you get or the frame that you get, you see, okay, it looks like as, okay, yes, it doesn't look like it. But it's going to, yes, okay, appear as you have a good focus at all the depths. So that's okay, this is electronic. Did you guys get that? So your phase delay is simply just going to be as okay, what is the time interval between stimulation of neighboring PCTs? So the greater the phase delay, the shallower the focal point. Okay. The shorter the phase delay, okay. Oh, sorry, the greater the phase delay, the shallow focal point, lesser phase delay, deeper focal point. Did you guys get that? Okay. So just look here. Can you guys see this picture here?
Yeah.
Okay. So pretty much okay as a picture, just like the transducer that we had the other day. And what I said was that this whole thing here. Okay. This whole surface here. That was your footprint. Because guys, tomorrow is okay when we start talking about is okay these individual transducers here is okay. One thing that I will be referring to is going to be is okay the footprint. Okay, but what we also can see is okay, or what we also is okay, or what we already just okay said was that the PCTs were going to be lined up like this along the footprint. And that's mean is okay why we call them linear, as I said earlier. Okay. Now, if you just take one PCT here, now he or she is okay. He's holding it a little bit weird. Okay. Anyways, but we guess that's okay. This becomes just okay, one PCT. I'm just magnified a little bit. Okay. But actually, it's okay. The way that we are going to be holding our transducer in most instances, that this here, this dimension here, that is going to be the height. Whereas on the other hand, we can say it's okay, this dimension, or let's say it's okay, this dimension, that is going to be the width. Okay, so one thing that we will see that's going to be as okay, contra to our round PCT or disc shaped PCTs is, because what we had here was, okay, is that the height and width were equal. That is not going to be the case here, because what do we have here? The height is greater than the width. Did you guys get that? So there's going to be some resolutions which will not be the same. Okay, guys. Any questions now? Any questions from some older chapters? Now, can somebody tell me what a channel is?
The electrical source plus the electrical wire plus the PZT.
Exactly. Okay. Okay. How many crystals did we have in a conventional transducer?
One.
What if we use this finger?
Still one.
Still one. Okay, good. Okay. Okay, guys. What will be your PRP if the depth of image is 3 centimeters? What is
39
the
microseconds. 39 microseconds.
39 microseconds? Good. Okay. What did we get as a result of destructive interference?
A smaller final wave.
Smaller in what sense? Smaller period?
No, shorter. Like, I never know how to word it. Like,
Okay, you forgot.
the
how to-
amplitude is
Smaller
less.
amplitude, right? Okay. Okay. So the bigness parameters is going to be lesser, right? Okay. Okay. Now we said that sound waves were mechanical waves, right? Or weren't they? Sound waves were mechanical waves. Why are they mechanical waves? Or what makes them mechanical waves?
Is it the medium that they have to pass through that makes them mechanical?
Okay. So what is it that we have in the medium then?
Particles.
Particles, good. Okay, now what happens to those particles? Mechanical.
They get compressed and rarefied.
Okay, so they go into
Motion.
motion. Good. Now, in which phase, whether compressed or rarefied, do we have the greatest amount of transfer of energy?
Compressed.
When they're compressed. Okay. What is the unit for temporal intensity? If I say it's okay, the temporal intensity is 2, what unit would you express it as?
Watts per centimeter square?
Good. Okay, don't fall for the time and say it's okay per second or something like that, okay? But not going to be watts per centimeter square per second or millisecond or something. Okay, it doesn't really matter whether you talk intensity or spatial intensity or temporal intensity, the units is the same. Clear? Okay. Good. In a non-imaging transducer, what was the greatest spatial intensity called? In a non-imaging transducer, what would be the name for the greatest spatial intensity? The phase delay is exceeding the allowed limits. Spatial peak. You guys got thrown off by me saying it's okay, non-imaging. Spatial intensity will still be there. The max spatial intensity will still be spatial peak. What's the difference between spatial, no, sorry, not spatial, temporal peak and pulse peak in pulsed wave transducer versus continuous wave transducer. What's the difference between the two? Spatial, temporal peak and temporal average and pulse average in a pulse wave transducer versus continuous wave transducer. Yes. Dr. O'Brien, you can speak out loud.
No, I was just hitting myself and saying, oh, that's chapter 5.
Okay, good. At least if it was open book, you know which chapter to look at.
Aren't they equal in a continuous wave transducer?
Mhm.
And
And
they're
what
not.
about our pulsed?
I know they're different. I can't remember the order right now.
That's when your pulse average was greater than the temporal average. Because temporal average includes the whole PRP. Whereas pulse average only includes, or is only as okay, the average for your on time. Clear? But since in a continuous wave transducer, all time is on time. The party never stops. There's no breaks. Okay. Okay. What's the typical value of a duty factor for a continuous wave transducer? Typical value of duty factor for a continuous wave transducer.
The 2 to 5,000.
How many?
Is it 2 to 5,000?
Chris, you missed continuous wave. That would be 100%. And 100% would be what? A duty of 100% equals what?
1.
1. So we could also say that the duty factor of a continuous wave transducer is 1. How is the thickness of the PCC related to the propagation speed of sound in the PCC? Anybody? I would say they are not related. Sure. Okay. How is the PCC's speed of sound related to the frequency?
The PCC thickness?
No. The PCT's propagation speed. How is that related to the frequency?
Directly.
Huh?
Directly.
Directly. Clear? Okay. Okay. Comparing the propagation speed of sound in PCT to that of soft tissue. What's the ratio? Of propagation speed of sound in piezoelectrical material or lead zirconate titanate versus that of soft tissue.
It's about 4 times greater.
4 to 5 times as greater as that of soft tissue. Okay, guys. Okay. So just look at these 2 topics here that we just did. The 2 transducers. Please read them. What we can say that they have in common is that they are both mechanically focusing, mechanically steered, sector-shaped images. They had circular around PCT or PCTs. And so, okay, well, where yes, okay, your annular array is still mechanically, I have more multiple focal points, which is going to be as okay. The focal depth is directly proportional to the diameter of the PCT. Okay, guys. Please read on, yes, okay, that first page of your transducers array, page 168. Look at things such as, okay, yes, make up your notes for your phase delay and the sequence and the juicy details of those. We'll start discussing that tomorrow. Okay, guys. Now have fun.
See you tomorrow.
See you tomorrow.
Okay.
God bless. God bless.